तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we shall consider about relation. What is a relation? In ordinary English and in ordinary life you talk about relationships. See, you have a collection of boxes and you say that one box is heavier than the other. That is a relationship among the boxes. And among human beings you say that one man is more intelligent than the other man. That is another relationship between men, the human beings. But you may also have a relationship between different sets. X lives in the city Y. You can have something like this: X lives in city Y, or X was born in city Y in the year Z. So, this brings out the relationship between different sets. X is a human being and Y is a city, Z is a year. So, you can talk about relationship between different sets, and in the ordinary sense you talk about the relationship like between the human beings. X is the father of Y, X is the uncle of Y. All those are relations and in the common sense of the word, and they also represent in the technical sense a relationship between the same sets of human beings. Now, why is it necessary to study about this? You know that in database management system you can retrieve a record, or you can find out something about the record and so on by searching a database management system. And in relational, there are several database management systems, and in relational database management system the whole thing is based on the concept of a relation, concept of a n-array relation. Everything is arranged in the form of a table where each table represents an n-array relations. Maybe I will mention about this a little bit later after we learn the definitions. So, it is very essential to learn the concept of relations. Also in several other places you talk about binary relations, that is an ordered pair, and in that ordered pair it will have some certain specific properties like reflexive, symmetric, and the condition that a relation should satisfy some of those properties is essential in many of the fields, especially in computer science, and we will learn about the applications where it is used as and when we come across the definition. Now, let us start with the definition of an ordered n-tuple and what is a relation, n-array relation, and so on. For n greater than 0, an ordered n-tuple or simply n-tuple with the ith component ai is a sequence of n objects denoted by a1, a2, a3, an. Two ordered n-tuples are equal if and only if their ith components are equal for all I. If n is equal to 2, the ordered n-tuple is called an ordered pair. If n is equal to 3, the ordered n-tuple is called an ordered triple. So, an ordered n-tuple a1, a2, it is represented like this, and if you have two of them, say b1, b2, Bn, you can say that these two are equal if and only if Ai is equal to Bi for all I. When you say ordered tuple, the order is very important. For example, consider the relation less and consider the ordered pair 3, 7. This would mean 3 is less than 7. If you change the order and write it as 7, 3, this would mean 7 is less than 3, and this is true while this is false. So, the order is very important. And similarly, when you say X lives in city Y or X was born in the city Y in the year Z, you represent it as a tuple X, Y, Z. That means X was born in the city Y in the year Z. X represents a human being, Y represents a city, Z represents a year. Now, if you say Y, if you interchange the order Y, X, Z, it does not make sense, because it will mean some city was born in X, that is a human being. It does not make sense. So, it will, if you represent it like this, X was born in city Y in year Z, you must write it as X, Y, Z only. If you write it as Y, Z, it does not make sense. For example, Ram was born in city Madras or Chennai, whatever it is, in 1972, something like that. This will be represented by the tuple Ram, Madras, 1972, and if you represent it like Madras, does not make sense. Madras Ram does not make sense. So, the order is very important. Especially in the case of relational databases, you represent them as tuples, as tables and tuples like this. You have employee number, name, salary, department, etc. So, this will represent a tuple. You may have other components also, and because of this you are able to define normal forms, etc. on relational databases. Now, before going further into the ordered tuple, let us consider what is meant by Cartesian product. Let A1, A2, A3, An be an indexed collection of sets with indices from 1 to n, where n greater than 0. The Cartesian product or cross product of the sets A1 through An is denoted by A1 cross A2 cross A3, etc. An, or x I is equal to 1 to n Ai. It represents the set of ordered n tuples. So, if you represent the Cartesian product, it is A1, A2, An, or you represent it as x I is equal to 1 to n Ai. In the case of set of this x was born in city Y in the year Z, you can represent it as A cross B cross C. A will represent human beings, set of human beings. B will represent cities. C represents years. This is known as Cartesian product. Again, if all the AIs are the same, for example, ordered pair represent the relation A. Here the ordered pair, if you represent as x, y, x is an integer, y is also an integer. In that case, A1 is I, A2 is also I, set of integers. So, you represent it as A cross A or I cross I here. In general, if A1, A2, An are all the same, you represent it as I is equal to 1 to n Ai is represented as A power n. Here it will be represented, because it is a less than relationship is on the set of integers, it will be represented by I square. Now, here again the order is very important. Let us take some example and consider what is meant by this. Suppose A is 1 and 2 and B is A and B, C is some alpha, D is phi, say. Then what do you mean by A cross B? What do you mean by A cross B? This represents ordered pairs where the first component will belong to A, second component will belong to B. So, it will represent 1 comma A, 1 comma B, 2 comma A, 2 comma B. What do you mean by A cross C? A cross C will be 1 comma alpha, 2 comma alpha. It will represent this. What do you mean by B cross D, where D is the empty set? In this case, this will be empty. And here again, the order is very important. Suppose you have A cross B, where A is the set of real numbers, between 1. That is, x belongs to A means it is a real number between 0 and 1, and y is a real number between 1 and 2. Y belongs to B. Both are real numbers. So, A represents the set of real numbers between 0 and 1, B represents the set of real numbers between 1 and 2. What does A cross B represent? X varies from 0 to 1 and y varies from 1 to 2. So, it will represent the set of points in this square. Now, suppose I consider B cross A, then it represents ordered pairs Yx. Now, the interchanging the order, the first component varies between x and 1 and 2, and the second component varies between 0 and 1. So, it will represent the set of points in this square. So, the set represented are different, they are not the same. So, here the order is important. A cross B is different from B cross A. So, commutativity does not hold, commutativity does not hold. What about associativity? Is A1 cross A2 cross A3 is the same as A1 cross A2 A3, A1, A2, A3 are sets. There is a slight problem here, because usually this, if x belongs to A1 y belongs to A2 and z belongs to A3, it will be represented as x comma y comma z, and this will be represented as x comma y comma z. There is a slight difference between these two, but usually in many cases you will try to write this as A1 cross A2 cross A3 without any problem unambiguous. But you have to be a little bit careful what you mean is correct. If it something is very particular, you want to represent only like this, then you have to represent like this only. But most of the cases without any problem we will be able to write as A1, A2, A3. So, we do not talk about the closure or and associativity. It is slightly tricky. The next definition is what is a relation. Okay. Before going to that, some relationship between the Cartesian product, union and intersection. This cross, if I say cross product, the cross distributes over union and intersection. A cross B union C is equal to A cross B union A cross C. Similarly, A cross B intersection C is equal to A cross B intersection A cross C. The other way around, A union B cross C will be equal to A cross C union B cross C, and A intersection B cross C will be equal to A cross C intersection B cross C. Let us prove this result. Let us take the first one and prove. The remaining can be proved in a similar manner. What is the first one? A cross B union C is equal to A cross B union A cross C. A cross B union C is equal to A cross B union A cross C. Let us see how we prove that. Now, when you say an ordered pair xy belonging to A cross B union C, this is equivalent to saying x belongs to A, it represents ordered pairs xy, x belongs to A, y belongs to B union C. That is equivalent to saying it represents a set of ordered pairs xy, x belongs to A, y belongs to B, or y belongs to C. Actually, here it is x belongs to A and y belongs to B union C, and similarly x belongs to A and y belong, this one you can write as y belongs to B or y belongs to C. That is equivalent to saying x comma y, this one and distributes over R. So, this one you can say as x belongs to A and y belongs to B, or x belongs to A and y belongs to C. You can write like this, and that is equivalent to saying it represents the set of ordered pairs x belongs to A and y belongs to B, that means x belongs to A cross B and y belongs to x belongs to A and y belongs to C, means x y belongs to A cross C. So, this one you can say as x y, x belongs to A and y belongs to B, or it represents the set of ordered pairs x y, x belongs to A and y belongs to C. and that is equivalent to saying x y belongs to A cross B or x y belongs to A cross C. That is equivalent to saying x y belongs to A cross B union A cross C. So, this proves the first part, and the second, third and the fourth parts can be proved in a similar manner. Now, let us see what is a relation. Now, we have seen what is a Cartesian product. A Cartesian product is denoted by x is equal to I is equal to 1 to n a I when you have n sets. Now, an NRS relation is a subset of that. For example, let us take A to be, as in the earlier case it is 1 2 and B to be say A B. Then A cross B represents the elements 1 A, 1 B, 2 A, 2 B. An n-ary relation is a subset of that. It need not contain all the elements, it can just contain some. For example, a relation R1 may be a subset of this, say 1B, 2A, or another relation R2 may just have 1A alone. Another subset may have 1A, 1B and 2A, like that. So, a relation is a subset of the Cartesian product. It is a set of, in this case we have taken ordered pairs, in general you can take n tuples. A relation R will be a subset of the Cartesian product I is equal to 1 to n A I. If it denotes that subset is the empty set, say if R is equal to phi, then it is called the empty relation or the void relation. The subset can be just the empty set also. And if the subset is the whole set, if R is equal to x, I is equal to 1 to n, R A1 cross A2 cross A2 A1 cross A2 cross A3 etc. up to An, then R is called the universal relation, all the elements are present. This itself represents a relation, and that is the universal relation. If n is equal to 1, 2, 3, it is called a unary relation. If n is equal to 2, it is called a binary relation. If n is equal to 3, it is called a ternary relation. So, for n is equal to 1, 2 or 3, R is called a unary, binary or ternary relation represented. A relation can be represented by a predicate. For example, you take the set of non-negative integers n, then you can say that an ordered triple x, y, z belongs to a relation R if x plus y is equal to z. The sum of the first two integers, non-negative integers, is equal to z. So, this is a relation on n cross n, where n is the set of non-negative integers. So, you represent the relation like this x, y, z. R consists of triples x, y, z such that x plus y is equal to z, and this is a predicate actually p x y z. You can represent by any predicate like that. For example, X was born in city Y in the year Z is a predicate. So, that represents a relation. So, a relation may be represented by a predicate like this. Now, in this case you can see that 1, 2, 3 belongs to R because 1 plus 2 is equal to 3. 2, 2, 5 does not belong to R because 2 plus 2 is 4 and you are having 5 here. So, this does not belong to R. So, it is a subset of n cross n. And when can you say that two relations are equal? You have one relation R1 which is an n-ary relation on x is equal to I is equal to 1 to n ai, that is A1 cross A2 cross A3 cross up to an, and R2 is an m-ary relation which is on A1 cross A2 cross A3 like that. Okay, we have taken it as Bi. So, it will be B on B1 cross B2 cross B3 cross Bm. So, you have two relations one n-ary relation on A1 cross A2, this is R1 An, and R2 is an m-ary relation which is on B1 cross B2 cross Bm. When do you say that these two are equal? When you say they are equal, when R1 is, when you say R1 is equal to R2, then you must have n is equal to m and ai is equal to bi for all I, and they should represent the same subsets, of the Cartesian product of x is equal to I is equal to 1 to n ai. In other words, if m and n are different, you cannot talk about the relations being equal, and when they are the same, they should represent equal subsets of the same set of Cartesian product. The underlying sets also have to be the same, then only you talk about the relations being equal. This, for example, here you have ABC, AB, and I have say C is equal to A comma B comma C. Then suppose R1 is on A cross B, and that is 1A 2B say. R2 is on A cross C and it represents the elements again the same 2 comma B. Even though they are same, you cannot say they are equal because the underlying sets are different. Okay. So, when you want two relations to be equal, they have to be defined on the same sets A cross B, and then they should also represent the same subsets. If R2 is defined on A cross B, then you can say that these two are equal. So, to talk about the equality of two relations, R1 is equal to R2 if and only if n is equal to m and ai is equal to bi for all I. That is, the underlying sets also have to be equal, and R1 and R2 are equal sets of ordered n tuple. They should represent the same subset of cross product of A1, A2, A3 up to An. Now, we are mainly interested in binary relations. Even though from the database management point of view, n-ary relations are more important, but for specific computer science fields, you talk about binary relations and binary relations satisfying some properties and so on. So, let us talk about binary relations. Binary relations will be on sets A cross B. Let R be a binary relation over A cross B. The set A is called the domain of R and B is called the codomain. We denote AB belongs to R by the infix notation ARB, and AB does not belong to R by A, R with a stroke B. So, if R is a relation defined on A cross B, then if you have an ordered pair AB belonging to R, you represent it as A related to B. If this ordered pair does not belong to R, you write it as A does not belong to R. This is the, for binary relation, this is the convention. Of course, you cannot extend this for ternary or other relations. Only binary you can use the infix notation. This is called infix notation. For example, take the less than binary relation. Then you can write, you say 4, 8 belongs to less than, that is 4 is less than 8. Usually you write it like this, or 7, 2 does not belong to the less than relationship, or 7 is not less than 2. Write like this. Okay. We have earlier seen that you can define a set inductively. What are the main points there? You define the basis class, which denotes the basic building blocks of the sets. Then you define the inductive class, which tells you how to build more and more elements from the already built elements of the set, and then you have an extremal class. If you look at the relations, they are also sets. Relations are also generally sets. They are subsets of the Cartesian product A1 cross A2 cross An in array relations. So, as a set you can define them inductively. That is, when you look at the relations as subsets of the Cartesian product, you can try to define them inductively. For example, let us see how the less than relationship can be defined inductively. Inductive definition of the less than relation. Now, this is defined on the set of non-negative integers into non-negative integers. We are not taking negative integers, just the set of natural numbers or non-negative integers 0, 1, 2, etc. How can you try to define this? The basis class is 0 is less than 1. you can also represent it as 0 comma 1 belongs to the less than relationship. Okay. Then how do you build the more and more elements of this relation? How do you define the induction class? It says that if x y okay, if x is less than y, then x is less than y plus 1 obviously. Also x plus 1 will be less than y plus 1, right. If you write in this notation, it will be if x y belongs to less than x y plus 1 belongs to less than and x plus 1, here also it is and x plus 1 comma y plus 1 belongs. Now, let us see how we get some of the relations. 0 less than 1, so you will get 0 less than 2, then from this you will get 0 less than 3 and so on, because making use of x less than y gives you x less than y plus 1. And when you consider this and use this, you will get 1 less than 2, then 1 less than 3, 1 less than 4 and so on. Make use of it, 2 less than 3, 2 less than 4 and so on. So, you will get all the less than relationship. So, this is a basic building block, and from this, by making use of this induction class, which tells you how more and more elements of the set can be built, or here more and more elements of the relation considered as a set can be built. You get all the elements of the relation. Of course, you have to mention the extremal class also. What does the extremal class say? It says that all the elements can be got from the basis and the induction class, and no other element will be got. Okay. So, you can define relations also inductively. Let us consider one or two more examples to see how to define a relation inductively. Consider this problem. For each of the following, give an inductive definition of the relation R on n. In each case, use your definition to show that the particular ordered pair X belongs to R. So, in the first example, the relation is defined as this A B, where A and B are non-negative integers and A is equal to 2B. So, you can see that the pair 6 3 belongs to the relation. Let us see how to define this relation inductively. So, the first basis class will be 0 0 belongs to R. You can see that 2 times 0 is 0. Then how to define inductively? The induction class will be like this. If xy belongs to R, then x plus 2 y plus 1 belongs to R. So, if xy belongs to R, then x is twice y, and if you add 2 to x and 1 to y, then again x plus 2 will be 2 times y plus 1. So, this is the way the induction class is defined. So, extremal class is the same for everything. Now, let us see how the ordered pair 6 3 we can derive from this. First, from the basis you have 0 0, then add to the first component and add 1 to the second component, you will get 2 1. Then do the same again, add 2 to the first component and 1 to the second component, you will get 4 2, then you will get 6 3. So, like this you can get the pair from the basis class using induction, and this is the way the relation R is defined inductively. Let us consider one more example. The relation R is defined like this. R is equal to ABC, where A plus B is equal to C. C is the sum of A and B. And you have to define this inductively and see that this particular triple 1 1 2 can be derived from the basis and the induction classes. So, let us see how we can define this relation R using basis and induction classes. Basis class will be 0 0 0 belongs to R, the sum of 0 and 0 is 0. So, this is the basis class, and how do we define the induction class? If x y z belongs to R, then x plus 1 y z plus 1 belongs to R. That means, if x y z belongs to R means z is the sum of x plus z is the sum of x and y, that is x plus y is equal to z. Now, if you add 1 to x, then the sum will be increased by 1, that is what is given by this. If x y z belongs to R, z is equal to x plus y, and when you add 1 to the first component, the sum should be increased by 1, that is the third component should be increased by 1. Also, keeping the first component the same, if you add 1 to the second component, then also the sum will be increased by 1, that is the third component has to be increased by 1. So, if x y z belongs to R, then x plus 1 y z plus 1 belongs to R, and x y plus 1 z plus 1 also belongs to R. This is the induction class. Of course, for all example, the extremal class is the same, it is the smallest set built from the basis using the induction classes. Now, let us see how this particular triple 1 1 2 can be derived from the basis and the induction classes. 0 0 0 belongs to R, that is the basis class. Then add 1 to the first component and 1 to the third component, that is if x y z belong to R, add 1 and 1 to the first and the third component, then you get this. Then by the second method, you add 1 to the second component and the third component. So, add 1 to the second component, 1 to the third component. So, 1 1 2 belongs to R. So, 2 is the sum of 1 and 1, that is 1 plus 1 is equal to 2, it belongs to R. So, you are able to derive this triple starting from the basis using the induction hypothesis. This is how the relation can be defined inductively. Now, a binary relation can be represented as a graph. A directed graph. What is a graph? A graph has a set of nodes, what are called as nodes or vertices. Nodes or vertices. Here A, B, C, D, E, F, G, they are all nodes. Then you have an arc between nodes. You have a directed edge, they are called arc or edges between the nodes, like this. Okay. So, a graph consists of a set of nodes and a set of arcs. A binary relation can be represented by means of a graph. That is what we consider next. A directed graph or digraph is an ordered pair D is equal to AR, where A is a set and R is a binary relation on A. The set A is a set of nodes, points, vertices of D, and the elements of R are the arcs, edges, lines of D. The relation R is called the incidence relation of T. Now, here there is one point we have to note, that we are taking the binary relation, a binary relation R on A cross A. we can take A cross B also. I will just in a moment come to that point again. Now, A cross A represents a set of elements. For example, take the elements 2, 1, 2, 3, 4, 5, and the less than relationship. We have already considered less than, so let me take again less than. So, 1, 2, 3, 4, 5, they will be represented as nodes. And then 1 is less than 2, so you have a directed edge between 1 and 2. 1 is less than 3, so you have a directed edge between 1 and 3. 1 is less than 4, 1 is less than 5, 2 is less than 3, 2 is less than 4, 2 is less than 5, 3 is less than 4, 3 is less than 5, and 4 is less than 5. So, this is a graph which represents the binary relation R among the set of integers 1, 2, 3, 4, 5. So, this edges, please remember that you need not have to have straight length, you could also draw like this, does not matter. You could also have a curved line. So, this is called a directed graphs because the edges are all directed. If you have nodes and connected without the direction, say something like this, this is called an undirected graph. Later on when we study graphs, we will talk about undirected graph also, undirected graphs. So, a binary relation on A cross A can be represented as a graph like this. Let us see the definitions once again. A directed graph or a digraph is an ordered pair where A is the set and R is a binary relation on A. The set A is the set of nodes and the elements of R are the arcs or edges of D. The relation R is called the incidence relation of D. Now, you may consider why we have taken A cross A. What happens if you consider A cross B? There is no problem. The ordered pairs, you can represent the elements of A and they represents the elements of B like this, and any ordered pair will be a directed edge from this side to this side like this. It can also be represented like this. Now, when you have a directed edge from a node to another node, from a node A to another node B, a directed edge like this, then A is the source node and B is the destination node. A is the source and B is the destination node. Now, in a graph from a node A, you may have say some 3 or 4 nodes starting from that. So, from A you may have some arcs leaving the node A, that is called the out degree of the node, out degree of the node. And for a node B you may have some arcs entering into it like this. The number of arcs entering into that is called the in degree of the node. If you have a node and an arc like this, this is called a self loop. Let D is equal to AR be a digraph. If A is related to B, then the arc AB originates at A and terminates at B. An arc of the form AA is called a loop. The number of arcs which originate at a node A is called the out degree of the node A. That is, the number of arcs leaving the node A is called the out degree. The number of arcs which terminate at A, or the number of arcs which enter into the node A, is called the in degree of the node A. Let us take some more examples when we represent binary relation as a graph. One or two properties of graphs. Now look at this graph, A, B, C, D, E. Then you say that A, B, C, D is a path. A, B, C, D is a directed path. Directed path. Let D is equal to AR be a digraph with nodes A and B. Undirected path from P, undirected path 3 from A to B is a finite sequence of nodes C0, C1, C2 such that C0 is A and Cn is B, and for all C, Ci such that I is equal to 0 to n, either Ci is related to Ci plus 1 or Ci plus 1 is related to C. For example, here I may have one, I may add one more arc like this, say like this. So A, B, C, D, E is undirected path, is an undirected path, because you have A, B, C, D is directed, because A is related to B, B is related to C, C is related to D. So A, B, C, D is an directed path, but you have E related to D, not D related to E. This path, if you consider, the direction changes here. So A, B, C, D, E is an undirected path, but A, B, C, D is a directed path. It may include the loop also. So you have A, B, C, D, D if you consider, that is another path. A, B, C, D, D, this loop you can go through several times, then E, this is undirected, and A, B, C, D, 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 B is directed, and so on, directed. Now in that path C0 to C1, if no node is repeated, it is called a simple path. If no node is repeated, it is simple. Now if you look at this B, C, D, B, you go back to, if you consider B, C, D, B, it starts and ends at B, but no node is repeated here. This is called a cycle. This is called a cycle. And if no node is repeated here, the beginning node and the end node are the same, but if no node is repeated in between, this is called a simple cycle. Let us consider this example. For each of the following, sketch a digraph of the given binary relation A. State whether the digraph is disconnected, connected, strongly connected, and state how many components. This portion we shall see after defining disconnected, connected, and strongly connected components. But let us see how to draw the graph for the binary relation. Take this particular example. The set consists of 1, 2, 3, 4, and there are 3 ordered pairs 1, 2, 1, 3, and 2, 4. So how do you draw the graph? It has got 1, 2, so there is a directed arc from 1 to 2. It has got the ordered pair 1 3, so there is a directed arc from 1 to 3. It has got the ordered pair 2 4, so there is a directed arc from 2 to 4. Let us consider the next example, xy, where xy can belong to 0 1 2 3 4, and the condition is that x should be between 0 and 3, y should be between 0 and 3, and x should be less than y. So, how do you draw this? The underlying set consists of 0 1 2 3 4. So, there is a node for each of the element of the set, and x, the ordered pair xy belongs to the relation if x is less than y and xy are between 0 and 3. So, there will be an arc from 0 to 1 because the ordered pair 0 1 will be there, ordered pair 0 2 will be there, ordered pair 0 3 will be there, the ordered pair 1 2 will be there, 1 3 will be there. These satisfy the condition, 2 3 also will be there. So, the arcs can be drawn in this manner. There is an arc from 0 to 2, there is an arc from 0 to 3, there is an arc from 1 to 2, there is an arc from 1 to 3, and then there is an arc from 2 to 3. Because the condition says that x and y should be between 0 and 3. If you have included 4 also, there will be more arcs, but it is not included. So, this is the diagram representing the relation defined by this. So, see, these are some of the basic terminologies about a graph. The main point here is that binary relations are represented as graphs, and we have seen a few terminologies about graphs. We shall consider more about binary relations and a little bit more about graphs in the next lecture.